Welcome to Two Projects. In this video, we are going to see a nonlinear regression application via machine learning techniques for geomagnetic data reconstruction processing. Introduction. Geomagnetic data which contains Earth's magnetic field is crucial for monitoring Earth's status, but missing data can cause serious issues. Various techniques have been introduced to overcome this issue, but they require heavy manpower and time. Machine learning, including linear regression, decision trees, SVM, artificial neural networks, and instance-based learning, is increasingly used in scientific fields for regression classification and clustering. Machine learning is being investigated for improving geomagnetic exploration, particularly in reservoir parameter characterization. Objective of the project. The project aims to create a machine learning based solution for reconstructing missing geomagnetic data using support vector regression, random forest regression, gradient boosting regression, and deep learning LSTM algorithms. The interface will be user friendly, allowing users to upload data, apply different algorithms, and compare their performance in predicting missing geomagnetic data values. Requirements. These are the requirements needed to execute this project. Hardware requirements: operating system of Windows, processor of i5 and above, RAM of 4GB and above, hard disk of 20GB and above. Software requirements needed are Python, ideally of Python 3.7 version. To execute this project, we have designed the following modules. The first module is Upload Geomagnetic Dataset. In this module, we will enable users to upload their geomagnetic dataset obtained from sensors. The provided data will contain information about the Earth's magnetic field readings, sensor IDs, and timestamp records. This dataset will be used for training and evaluating the algorithms. The second module is Run Support Vector Regression. In this module, we will apply the support vector regression SVR algorithm to the uploaded dataset. SVR utilizes support vector machine principles to predict continuous values. SVR will be trained on past data to predict missing values in the dataset. It aims to fit a line within a defined error threshold to predict the missing values accurately. The third module is Run Random Forest Regression. Here we will employ random forest regression, a technique involving multiple decision trees. Each tree provides its own prediction, and the final result is an aggregate of these individual predictions. The algorithm prevents overfitting by limiting the number of features considered at each node and using random sampling of data to build the trees. The next module is Run Gradient Boosting Regression. In this module, we will utilize gradient boosting regression, which sequentially builds multiple weak models and combines their predictions to improve accuracy. This approach adjusts the weight of each model based on its errors in previous iterations, creating a strong ensemble prediction. The next module is Run LSTM Deep Learning Algorithm. Here, the Deep Learning Long Short-Term Memory LSTM algorithm will be employed. LSTM is well suited for sequential data like time series due to its memory capability. We will train on LSTM model to predict missing values in the dataset by learning patterns and dependencies from historical data. The next module is Upload Test Value and Reconstruct Data for Missing Values. In this module, users can upload a test dataset containing values with missing targets. The algorithms trained earlier will predict the missing target values based on the provided input features. This step showcases the predictive capability of the algorithms. The next module is RMSE Comparison Graph. This module generates a graph displaying the root mean square error RMSE for each algorithm's predictions. RMSE quantifies the difference between predicted and actual values, providing insights into the accuracy of the algorithms. The next module is 2D Geomagnetic Data Graph. In this module, a graphical representation of the original and predicted geomagnetic data will be generated. This visualization aids in comparing the performance of different algorithms in capturing the underlying data patterns. The last module is Accuracy Graph. This module generates a visual representation of the prediction accuracy of each algorithm. This graph allows us to understand the varying accuracy levels of different algorithms when predicting missing values in the geomagnetic dataset. Execution of the project. To execute this project, first we need to open the code folder. This is the dataset folder in which I have required dataset and test dataset. I'm opening the required dataset. So here This dataset contains magnetic field data, timestamps and sensor IDs for the Hyderabad area. Recording every minute, missing half-minute values will be forecasted using regression algorithms trained on historical data, revealing magnetic field patterns. Close this dataset, and this is the test data on which we will predict missing values. This is the Python main code file and this is the run.bat file. Instead of executing the project in command line interface, we have created this Windows batch file. Double click on run.bat file. This graphical user interface will be opened. With this, we are interacting with the program. We have used Tkinter library to create this graphical user interface. Now click on Upload Geomagnetic Dataset button. A dialog box opens. Select the dataset and click on Open. So in the text area, we can see a confirmation that dataset is loaded. Now click on Run Support Vector Regression button. So here, total dataset length contains 314 records, and this total dataset is split into train and test sets in the ratio of 80:20. Now train set includes 251 records and test set includes 63 records. Train set is for training the models and test set is for evaluating the performance of the modules. And here we can see the support vector regressions, RMSE and accuracy. Now click on Run Random Forest Regression button. So this is the RMSE and this is accuracy of random forest regression. Now click on Run Gradient Boosting Regression button. So here we can see the gradient boosting regressions, RMSE and accuracy. Now click on Run LSTM Deep Learning Algorithm button. So in the console we can see the epochs are being calculated, and here we can see RMSE and accuracy of LSTM model. Now click on Upload Test Value and Reconstruct Data for Missing Values button. A dialog box opens. Select the test dataset and click on Open. So here these are the input values and these are the reconstructed missing values. Now click on RMSE Comparison Graph button. So in this graph, on x-axis I have the algorithm names and on y-axis I have the RMSE, and we can see LSTM algorithm has got the least RMSE. Close this graph and now click on 2D Geomagnetic Data Graph button. So this is the 2D Geomagnetic Data Graph of original and predicted geomagnetic data. Close this graph and now click on Accuracy Graph button. So in this graph, on x-axis I have the algorithm names and on y-axis I have accuracy, and we can see both LSTM and SVR have got the highest accuracy. Close this graph and the conclusion here is this project introduces a new method for predicting missing geomagnetic data using machine learning techniques. It uses support vector regression, random forest regression, gradient boosting regression and deep learning LSTM algorithms. The interface simplifies data upload, algorithm comparison and performance evaluation. The results highlight the importance of algorithm selection in accurately reconstructing missing geomagnetic data, providing valuable insights for data scientists and researchers.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.